Alright, welcome to 5-1 video 4. We're going to talk about some polynomial geometry. So we'll start with this example here. It says determine an expression that would represent the area of the figure shown below. So remember what area is. Area is just multiplying length times width, or base times height. It is two dimensions being multiplied together. So for this one, I have this dimension here, which is 3x plus 7, and this dimension here, which is 6x minus 5. And really, this is no different from any other of these polynomial problems that we've been doing whenever we're multiplying, specifically the section where we were multiplying a binomial times a binomial. And you're just going to multiply those just like we did in those problems. So let me set this up here for us. So 3x plus 7, and I'll use a set of parentheses, and then 6x minus 5. And then I'm going to set up a box so I can do my area model. And I'll write 3x plus 7 and 6x minus 5, and then I'll just do some multiplication. So 3 times 6 is 18, x times x is x squared. 3 times negative 5 is negative 15, and then bring the x with it. 7 times 6 is going to give us 42, bring the x with it, and then 7 times negative 5 will give me negative 35. And now again, like I said in the last video, when you have these in standard form, these binomials in standard form, which they are here because this is the highest exponent here, this is the highest exponent, and then this is the constant, the diagonals end up being like terms. So I know that 18x squared isn't going to combine with anything, so I'll type it here, or write it here, 18x squared. And I know that negative 35 won't either, so I'll write it right here because there's no other like terms with it. But 42 minus 15 is going to give us 27x. So my final answer for this is 18x squared plus 27x minus 35. And that's how you would find the area for that. It's going to be represented as a polynomial expression because we have 3x plus 7 here as one dimension and 6x minus 5 as the other. All right, let's look at another example. So I like to call this one, personally, I like to call this the pool problem because it reminds me of a pool, and I know that maybe this is kind of a skinny looking pool here. If you kind of use your mind's eye to think of this area here as the pool, and then the gray area on the outside is like the sidewalk that surrounds the pool. But I like to call this the pool problem because we want to know the area of the shaded section on the outside here. And we really have to think about this a lot more simple at first. And so in order to find just this area that's shaded, I want you to think about this as two separate rectangles. And the area of just the shaded part is going to be the big rectangle minus the small rectangle. Okay, so I'm going to say the area of the big rectangle minus the area of the small is going to give us the shaded area. Okay, so let's figure out how to do that. Well, it looks like I can easily find the area of just this little white space here, and that's just going to be 12 times 7. So 12 times 7 is going to give me 84 units squared, so I'll leave that there. So I know the area of the smaller one is 84 units squared. But what about the area of the bigger one? Because it's showing me that this length right here is x, and I know that this is 12 and this is x, so how would I find what the length of this outer edge is? Well, unfortunately, it's not going to be just a number, it's going to be an expression. And we know that because I know that this is x, which means that from here, let me get my eraser out real quick and erase this. Because I know that from here to here is also x because this distance is x. Same thing here, this is x. And I also know that if this from here to here is 12, then the distance from here to here is 12, meaning the entire distance from this outer edge to this outer edge is 2x plus 12, because I have how many x's? I have 1, 2, plus 12. So I'm essentially just combining like terms here. I have 2x's plus 12. So the expression here is 2x plus 12. And I can do the same thing for the other side here. I know that this has to be x because this here is x. And I know that this has to be x right here because I know that this is x. And if this is 7, then the distance from here to here is also 7. So hopefully you're starting to see here that the length of this outer edge here is 2x plus 7. And now we have a way to find the area, and I know it's not an actual number, but it's an area represented as an expression times an expression, and then we can find the area of the bigger rectangle. So let's do that. Let me change colors here. So in order to find the area of the big rectangle, I will do 2x plus 12 times 2x plus 7. And I always like to use that area model because it organizes everything for me. So I'll put 2x and 12 here, and I'll put 2x and 7. And we'll just multiply. So 2 times 2 is going to be 4. X times x is going to be x squared. 2 times 7 is going to be 14x. All right, and 2 times 12, 2x times 12 will be 24x. And then 12 times 7 is going to be 84. And again, these diagonals are going to be like terms because our polynomials on the outside, we put them in standard form here. So 24 plus 14 will give us 38. So the area of the bigger rectangle, let me say is 38x, is going to be 4x squared plus 38x plus 84. Okay, that's all of this added together. So 4x squared plus 38x plus 84. Now, I have to do some subtraction, right? Because we know that if the area of the bigger rectangle is this expression and the area of the smaller rectangle is 84 units squared, I have to subtract them to get what just the shaded area is. So if I just subtract the 84 that we got here, these will cancel and my final answer will be 4x squared plus 38x. Technically it's units squared, but this is my expression that represents the area of this shaded region here. All right, you have a U-try that you can try, and then I will see you in the next video.